So if we have kind of the saga of AlphaGo, it really started in 2016, where everyone heard of AlphaGo playing this tremendously exciting series against Lee Sedol, and it won 4-1. This was the first time a computer Go program ever beat a top professional player, and this was just unprecedented. No other program came close. And this was an achievement in computer Go that was categorically unlike anything that had been done before. And this was incredible, but it still relied entirely on human knowledge as its base. It trained on the knowledge it was given from human games to initialize the network. It relied on features that were designed by its human engineers, and it learned through self-play, but it did so through the lens of these human features it had been given and starting from these human games it had been given. So then AlphaZero was the beginning of this whole new paradigm. AlphaGo Zero was trained only through self-play, as Henry discussed. There were no human features, no human inputs. Everything was determined by the agent itself. And so it was philosophically, an entirely new regime compared to the original AlphaGo. Even though AlphaGo itself, was already beyond what human players could do. And so the next step was to say, well, okay, we've shown that Go can be mastered by a computer through self-play with no reliance on human input. Well, what about other games? Can we make an algorithm that will allow a computer agent to learn any game without needing to tune the algorithms to the game? Make one algorithm for any game, and it will learn any game to the state of the art and beat any other computer or human agent in the world. And DeepMind's answer to this was AlphaZero. So AlphaZero was an extension of AlphaGo Zero to chess and shogi. I'll give it a second more. And again, generalized to these regimes using only self-play and achieved world-class performance in each regime. The algorithm was not tailored to the specific game. It was the same algorithm for Go, chess, or shogi. The only changes were the input features and output features of the network in terms of what the valid moves were that you could make. For example, the size of the board, what the pieces were, etc. So I'll discuss a little bit about each game. I'm not going to spend a lot of time on this because I'm sure everyone's heard of chess already. But just in case anyone hasn't, it's possibly the most popular and widely played strategy game in the world. The only competition would be Go. It's turn-based like Go, 2 players, each controlling a different set of pieces, completely observable if you take into account the history. And it's played on an 8x8 board rather than 19x19. Each player controls 16 pieces, where there's pawns, knights, bishops, rooks or castles, a king and a queen, and they all have different rules for how they're allowed to move and capture on the game board. Your goal is to capture your opponent's pieces and eventually checkmate, where checkmate is when you put the opponent's king into a situation where it cannot avoid capture no matter what it does. So this is the base chessboard, the white pieces and black pieces. White moves first, and a sample move might be moving a pawn forward like this. So shogi is, at least to me, a little bit less familiar. I think it's a Japanese game primarily. It's very similar in concept to chess, though. It's a 9x9 board instead of 8x8. There's different pieces than chess, but they're very similar. Pawns are in both games. Though chess pawns capture diagonally forward, whereas shogi they capture directly forward. There are knights and rooks. The only major difference in philosophy in shogi is that a lot of the pieces can only move forwards, and not all of them, but most of them. And then they promote near the end of when you get to the opponent's end of the board, and then they gain a new ability to move that allows them to move backwards. And also, captured pieces from your opponent can be returned to the board under your control. So this is what a shogi board looks like. Unlike chess, there's no white and black pieces. You figure out whose piece is whose by the orientation. So if it's pointing this way, it belongs to this player. If it's pointing this way, it belongs to that player. You have pawns, gold and silver generals, knights, lances, rooks, a variety of pieces, but all similar in spirit, if not in detail, to chess. I'm going to spend most of my time in this presentation talking about chess because it's the game that's more familiar to me, but everything I say about chess is going to apply essentially the same to shogi because they're quite similar games. So the history of chess for computer methods. I'm sure everyone's heard of the Deep Blue chess agent that faced Garry Kasparov in the 90s and beat him in a 6-game set. And this was the first time that a computer agent had beaten a top human professional at chess. And in the roughly 20 years that's passed since then, we're now at a point where Deep Blue was originally run on these massive banks of machines, and it was this cutting-edge algorithm developed by IBM. Whereas now, I can download an open source chess agent off the internet, and I can play it on my laptop, and it'll be better than Magnus Carlsen, significantly. So we're kind of in the beginnings of this era when it's coming to Go. We're not quite there yet. Right now, we're still running on Google TPUs, and probably can't download it off the internet to run on my laptop, but we're working on it. So Shogi is similar. It took a little bit longer. It took until 2013 for Shogi engines to defeat top human professionals. But chess and Shogi were both unlike Go in the sense that they didn't require this very, broad, sophisticated reinforcement learning algorithm in order to defeat humans. They were able to defeat humans with a much more, I guess, simplistic approach in the sense of grounded in, these handcrafted features, doing searches and having these memorized books of positions in terms of opening positions and endgame positions. And so part of the reason for this is that Go, while it's similar to chess and Shogi in that they're both board games played on a 2D grid where you play pieces and have a similar kind of feel or style, Go is much, much, much more complicated than either chess or Shogi. Go has 10 to the 174 estimated board configurations. Chess has about 10 to the 120. Now, we as humans look at those, it's 10 to some huge number. One's bigger than the other. It's not that much bigger. Well, a factor of 10 to the 50, that's, billions of billions of billions of billions of billions times more complex. It's undescribably more complex than chess. And Go is also more uniquely suited to a reinforcement learning approach. Go's rules, the fundamental rules of Go, are very simple, but the strategy that arises out of them is immensely complex. Its board is extremely symmetric. There's 8 symmetries for each valid board position of Go, and this can be exploited for data augmentation, where you can create copies of each transformed version of the board to train on, which allows for better data efficiency. In addition, all interactions in Go are local to do with adjacent pieces and liberties, and all the rules are translationally invariant, with no position-dependent rules. And these can both be leveraged in the structure of a convolutional neural network to it matches very well to the inherent structure of a convolutional neural network, which also shares these same local properties and symmetries. That so it kind of is in some ways inherently well matched to the problem of Go. Now in chess, this isn't true. Chess has position-dependent rules. If my pawn is on the second rank, then I can move it forward 2. Otherwise, I can move it forward 1. So those things aren't true. But on the other hand, its search space is so much smaller. Like we talked about branching factor with trees last time. Go has an average branching factor of 250. Chess has an average branching factor of 35. So the ability of a computer program to search through the entire search space of a chess game is much more feasible, much more tractable than it is for Go. So you can have these agents that rely much more heavily on brute force search and still perform very well at the level of top human players, where you can't do that in Go. So the top chess and Shogi algorithms basically rely on 3 things: handcrafted features, alpha-beta search, and memorized books of positions. So we'll talk a little bit about alpha-beta search, though we talked about it last class, so I won't go too much in detail. But you have a variant of general minimax search, where you're doing a search over all positions, where you're saying, how can I best minimize the maximum value of my opponent's actions? Or how can I best maximize the minimum value? Because the idea is at each stage, each player is assumed to play optimally. So I know my opponent is going to take the action that is best for them, and I want to minimize what the value of that best action. Or my opponent is going to minimize the best value of my action, and so I want to maximize that minimum value of my action. And that's the philosophy behind Minimax Search. Alpha-beta search says, okay, this is great, but we get a huge search tree very fast because we consider all these different possibilities. So in order to make this tractable, we have to scale it down. So we prune away branches that are dominated strictly by other branches, which means we have some kind of evaluation function to evaluate a branch. And I say, if this one branch is going to be worse in its valuation than this other branch, no matter what I do, then I won't even consider it. Just get rid of it. I lose nothing, but I make my search tree more tractable. So that's the idea behind alpha-beta search. We went into detail last class, so I won't go into more detail now. The second thing they do these programs do is they have evaluation functions based heavily on handcrafted features. So for chess, for instance, they'll use handcrafted features like assigning point values to each piece. And they'll have different sets of point values for different stages in the game. They'll have metrics to determine what the stage of the game is. They'll have heuristics to evaluate piece mobility or how safe your king is. And they'll combine these features to evaluate given states. And they'll use a huge number of these handcrafted features. And so as an example, these are point valuations by, oh gosh, what's his name? I forget the name, chess grandmaster whose work became the foundation of most computer chess engines in terms of point valuations. Unfortunately, I don't have the versions broken down by game state. I couldn't find those, but this is what I do have in terms of the values of various pieces. And so the last thing they'll have that's very important is they'll have opening books and endgame tables. So for endgame tables, the program will, in advance before the game, not during inference, they'll go and they'll record all possible endgames, every endgame that you could possibly play out with, say, 6 pieces or less. And they'll save those in these giant compressed databases. And they won't run this during the game. But during the game, if they get to one of these positions, they can look up the appropriate move in the table to always be guaranteed to play optimally. Now, the much more important one of these endgame books, they're obviously nice, but the much more important one is opening books. Because the worst position in the game for a chess engine is the opening. Because if you have a chess engine that's relying mostly on this brute force search, you search maybe 10 moves, maybe 50 moves, who knows, some depth into the future, but you can't search the entire game state. And your opening moves dictate the tempo and structure for the entire rest of the game. So if you can't really search directly to see what the outcomes of all your moves will be. So it's difficult to get a good valuation for your opening positions without some kind of extra information, just because they will have such long-term implications. And so that's why you have these opening books that will be stored various openings with various evaluation metrics, statistics, histories, etc., that they'll use to help pick an opening move. And again, everything I'm saying for chess engines also applies for Shogi. They're very similar. So AlphaZero's approach is very different than this. AlphaZero, the AlphaZero algorithm in general is basically the same as the AlphaGo Zero algorithm that Henry presented. It differs only in some very small details. It's trained through self-play with reinforcement learning, starting from a state of zero knowledge, a tabula rasa. It's given the rules in terms of its input and output features, but no handcrafted features made by humans and no prior experiences or human training data. Its algorithm relies on a deep neural network with a Monte Carlo tree search, and it performs basically policy iteration with a policy evaluation and a policy improvement step. It evaluates the policy with anchored to a deep neural network, and the neural network will evaluate the probabilities of each move being played and the value of the current game state. And then it'll expand this using a Markov tree search with simulated self-play to evaluate the current policy at the current state. Now for training with policy improvement, they'll use the search probabilities discovered by the Markov tree search, backpropagated to the root node, and then they'll compare the probabilities generated by the neural network itself at the root node to the probabilities found by the search. And they'll say, well, the probabilities found by the search look farther into the future, they should be better. And so they train using a combined loss function that I'll get to later to maximize that. So for the deep neural network acts as a function parameterized by theta, which produces a vector p of probabilities over valid moves, and a value v, which is a scalar to represent the expected value of the game. For AlphaGo Zero, this is interpreted as a probability of winning, but because Go does not have draws. For chess, it also incorporates the possibility of a draw. And this represents both the policy and the value. So it's not, it's sort of a combination, I guess you could say. It's not strictly like a policy gradient approach or a deep Q approach, because it explicitly models both the policy and the value. And it models them both with one network, rather than two networks, such has been done in the past, like Henry discussed. So the architecture of the network is basically residual blocks. If you're familiar with convolutional networks or computer vision, this will be very familiar. Each block is 256 by 3 by 3 convolutional layers, followed by a batch norm and a ReLU activation. A skip connection is added to connect the block's input to the output of the convolutional layers, followed by another ReLU activation. So this is, I won't go tons into the deep learning side of this, but the idea behind using residual networks is that it lets you propagate the gradient through the layers of a very deep network much more effectively because of the skip connections. And as Henry discussed, the use of residual networks over pure convolutional blocks added at least 600 ELO to the effectiveness of AlphaZero. So it's absolutely critical that they use these residual blocks. The network consists of 20 blocks. I think they also had a 40-block version. And then after these blocks, they had a policy head and a value head, which basically are a transformation that map from this the space produced by this convolutional network into the space of the probability vector or the just scalar for the value. The inputs and outputs features are in the form of n by n planes, where n is the board size for the game, so 19 for Go, 8 for chess, 9 for Shogi. Each input plane, essentially, is associated with a particular piece in the game and has a binary value for that piece being present or absent. So you'll have a plane for each piece owned by each player. I'm talking from the perspective of chess here, really. And it'll be a 1 if there's a piece there and a 0 if there's no piece there. And then each output plane is associated with a particular possible action. So for example, in chess, you have 8 directions of movement. And so we'll have basically, say the first plane might be associated with moving forward 1. And so the value at each square is interpreted as the probability that the piece at that square will take the type of action determined by that plane. So each plane might be associated with one action, such as moving forward 1, moving southwest 3, etc. And the idea would be that if that's not a legal move, for example, if there's no piece there, or if the piece that's there cannot take that move, the probability must be 0. So here we can show the features for each of the 3 games. And so these are all the different features that you need for the games. So if you use, this is using a history of 8. So you take these values added up at the top, multiply them by 8, and then add these final features, which are basically extra features in addition to the pieces that can't be observed just in the pieces. So for example, what color the pieces are, like what color the current player is, whether or not you're allowed to castle, the total number of moves, things like that you can't observe just from the board position. And this is the total number of input planes for each network. And for the output planes here, we have 73 for chess, 139 for shogi. And these are representing all the different possible actions. So the first 56 planes are all the possible queen moves in each of the 8 directions for chess. And then the next 8 are all the possible knight moves. And then some planes related to promotions. So now the Markov tree search. So we expand, Monte Carlo tree search. I always say Markov chain instead because I'm used to MCMC. At each stage, you evaluate one of the child nodes, expand it based on the most promising node, and they use a upper confidence bound or UCT style algorithm for this to encourage exploration. I believe the specific algorithm is PUCT, is polynomial UCT or something like that, but I didn't go into all the details. Oh no, my spaces around my theta were deleted. Then the network parameters are trained to essentially on a twofold loss function. You want to basically train on the squared error of the value versus the actually observed value at the end of the game. And you do a cross-entropy loss of the search probabilities, which are taken to be something akin to the ground truth, or at least closer to the ground truth. And then the actual probability is predicted at that stage by the network, with also a term for a weight decay to minimize the act as regularization. And the way the training is performed is at each iteration, they'll generate a massive number of games of self-play on all these TPUs, the incredibly powerful computers Google has. And then at the end of that, they'll go and train using this loss function with mini batches from states from those games of self-play generated at that iteration. So differences from AlphaGo Zero. One of the things AlphaGo Zero did, I believe, is they would replace the old player with the new player after it achieved a 55% win rate, whereas AlphaZero just trains continuously. At each iteration, you update the network. There's no testing to see whether you've gotten better. You just assume you've gotten better, update the network at each stage. They have to incorporate draws, so the V value that the network produces can't be interpreted just as a probability of victory. It has to be interpreted as an expected outcome over win, loss, draw. There's also the symmetries I mentioned before. So in AlphaGo Zero, specifically for Go, everything was symmetric with these 8-fold symmetries of the Go board. And so you could augment each state through data augmentation by duplicating it 8 times according to these rotational and reflectional symmetries. But you cannot do that for chess or shogi. So here's some statistics on how the training was performed. Number of mini batches evaluated, number of training games, training time for each, thinking time. So you can see Go is by far the longest and chess was the shortest, which makes sense because chess is the simplest of the 3 games and Go is by far the most complicated. And then some results. So they played AlphaZero against previous versions of AlphaGo Zero. Shogi, they played AlphaZero for Shogi against the top computer agent Elmo. And for chess, the matches were between AlphaZero and the top chess agent Stockfish. And so you can see AlphaZero did exceptionally well, winning 28 chess games, drawing 72, and losing 0. In Shogi, it won 90, drew 2, and lost 8. Now for Go, it's playing against the previous version AlphaGo Zero, and it's not that different, so the record wasn't quite as amazing, but it's still pretty impressive if you consider the progress they've made. And this is, you can see the results as a function of the training time. These are graphs of ELO. So ELO is a common system for ranking players across many different games. They have some complicated formulas of how it's determined. I think in the AlphaGo Zero paper, they stated that a difference of 200 ELO should represent a 75% win rate of the higher versus the lower. And so you can see, AlphaGo Lee was already at the level of top human players. And AlphaGo Zero, or AlphaZero, are so far above that it's like there is no comparison between AlphaGo now and human players. Whereas in chess, if you compare to Stockfish, AlphaZero is better than Stockfish, but the difference is much smaller. And I might get into that a little bit more later. And so these are training times in terms of seconds per move. And ELO. Oh no, this isn't training time. This is scalability in terms of how well the network performs when given extra training time compared to the others. There's another graph that I don't think I put in here that shows essentially, how many positions AlphaZero evaluates per second. AlphaZero evaluates on the order of 10,000 or 40,000, something like that, positions per second, whereas Stockfish evaluates 30 million. But AlphaZero is so much more efficient in its evaluation because it can focus on only the best of these positions to expand, only the best positions to focus on, whereas Stockfish simply looks through everything. It's part of the difference between a Minimax search and a Monte Carlo tree search. How am I doing for time, by the way?
Maybe just a few more minutes.
Just a few more minutes? Okay, I'm almost done. So in conclusion, after 44 million games of self-play, it achieved state-of-the-art play for chess, winning 28 out of 100 and drawing the other 72. With 24 million games of self-play, it defeated Shogi engine Elmo 90 to 2-8. And AlphaZero uses no human knowledge, trains only through self-play, and only the form of the input and output features changes between games to represent the game's rules. Nothing else in the algorithm changes. It's fully general. Should I wrap up, or could I have time for one more slide?
Yeah, one more slide.
Okay, so the one other thing I feel I really have to mention is while this was an incredible achievement, specifically the achievements in chess have been criticized by a number of chess experts because they claim that their agent AlphaZero does defeat Stockfish handily and is 28-72-0, the better agent. But there's a lot of questions about these matches because Stockfish was not given access to an opening book. And as I mentioned previously, traditional chess agents are heavily, heavily reliant on opening books to be able to play optimally. They also played with fixed time controls, whereas the standard chess time controls are you're given a total amount of time for the game and you can spend that however you will. And Stockfish is designed to optimize and spend most time on the moves that matter most. They also used a year-old version of Stockfish and made arguably suboptimal choices for hyperparameters, given the amount of computational power they gave the agents. And so to sum up, this quote was just so wonderful that I could not leave it out of this presentation. And so this is Hikaru Nakamura, a chess grandmaster's opinion about the Stockfish versus AlphaGo match. He said, God himself could not beat Stockfish 75% of the time with white without certain handicaps. So I don't know where he's getting the 75% number. Maybe he's counting the draws as like half or something like that. But so there are questions about the chess matches, but it's still, no matter what, it's an incredible achievement by AI that's really unprecedented by any other artificial intelligence agent ever designed.